the last two things that we need to do is differentiation and integration of trig function. So, to show you differentiation, to put up with bio from GeoGebra, we got our, I'll change this, start looking at sine of x. Alright, so there's our sine curve. So we've got our radian measure on the bottom. Okay, so pi on 2, pi, 3 pi on 2 and 2 pi of course over here. What we're going to do is going to trace this point A through the sine curve. This point here, A prime, okay, is going to have the same x coordinate, but the y coordinate is going to be the gradient of the tangent at that point. Okay, so we form a right angle triangle. Of that side always going to be 1, and then that side going taking the displacement, not the distance. Okay, so the displacement changed from the origin, so this one we're going in the negative direction. Okay, that means the gradient is going to have it's going to have a gradient of negative 0.38, so that's going to be that slope. Okay, so considering that drop and the run as well. So negative 0.38, so plotting that on your y-axis, so it's just below the origin there. Okay, so as we change that, okay, we're going to get that change in that point there. So when we have a horizontal tangent there, okay, so the gradient is 0. So on the we've got the x value of pi on 2, and the y value is going to be 0. Okay, so what I'm going to do is I'm going to continue looping, following that path, and we're going to see what function it traces here. Before I do that, any ideas on what the function, the derivative function is going to be? Good. Okay, so if I continue tracing, so we're following that green one. Alright, so at the origin I'll have a tangent of 1. Okay, so we've got a maximum amplitude in this case here. Alright, so continue following. Okay, that way. And I'm going to have the general properties of my cosine curve.
So why does the line break?
So?
Why does the line break?
Oh, because it's trying to map an infinite number of points to produce the curve, so it wasn't going slow enough for it to map there. But the general pattern of the curve, okay, can everyone see it's a cos curve? Because this is 1, alright, and it follows that pattern of the cos curve. Alright, so the derivative function of your sine function is the cosine function. Okay, so that's our first result. So, d dx of sine of x is cos of x. Okay, so differentiate sine, get cos. Okay. Now, generally speaking, so d dx of sine, some function of x within the sine, okay, is going to equal that derivative of inside the bracket of cos of f of x. Okay, extending that. Right, so let's now look when it's cos. Alright, so there's our cos curve, so we just mapped out that point there. Okay, any suggestion before I map it out what the derivative function is going to be? Oh, you're clever, aren't you? Alright, so those can't see it straight away, so following it now. Alright, so what we are doing is we're mapping the same x value, but the y value for the green part is the gradient of the tangent at that point. Okay, and that's what we are plotting. Alright, so it continues over that side, and we've got that wave pattern happening there. Okay, and it's really a reflection of your sine curve, because your normal sine curve is something like that. Oh, poor John. Because it's so wide. There, okay, so that's your normal sine curve. But you've got the negative. So you've got your y value, instead of being positive, is negative in your first two quadrant, and the y value here is positive in the third and fourth, as opposed to being negative when you consider your all students take calculus there. Okay, so that's your second result. So that's number one. Number two, so d dx of cos of x is negative sine of x. Okay, we can do a proof. It will involve differentiation by first principles. Might ask you to do that for an exercise tomorrow. D dx of cos of some function of x. Okay, so it could be cos of x squared plus 3, for example. Okay, that will work. Okay, when we differentiate, we're going to have the first derivative of that function after the cos. Okay, so it's going to be negative out the front because it's negative sine of f of x. Right. Any questions so far? Okay, so it's been proved by differentiation by first principles. Okay, so you can take my word for it now. Okay, so now do 10.
Wow.
Take 2. Alright. So remember tan itself is not a function because you have the asymptotes there. Okay, so we don't going to fail the vertical line test. Right. However, we can still differentiate as long as we limit the domain. Okay. So just trace it. And that A here is coming down from the top because at the moment we've got a positive gradient, and of course the gradient here is much steeper compared to when you get closer and closer to the origin. Right, so that's why you've got some very high value for y as you get further from pi on either side. Okay. And what do you notice about this one? Looks like a parabola, doesn't it? What else do you notice? Hey?
It's too brown for a parabola.
So it's not a parabola, alright, but it does look like one. It's good, but what else do you notice in terms of the gradient? So it's always above the x-axis because it is always positive. Okay, so that is going to be the derivative function. So of course, as we get further and further away from pi, right, the gradient, if we draw a tangent there, is going to get steeper and steeper. Okay, so of course, at pi, we'll do the math there, we can get 1. Okay, so there's the amplitude, sorry, not the amplitude, there's the y value 1 here, which matches there, and then it's on either side. Now, can we all see, because this is all the same curve, just in different positions on your x-axis, that this is just also going to have the same sort of thing happening on each of those. Alright? Now, the derivative. Okay, so again, proved by first principles. So d dx of tan of x. Do you know this one?
Sec squared.
Oh, you're clever, aren't you? So the derivative of tan of x is sec squared of x. So sec is the reciprocal of cos. Alright? So d dx of tan x is sec squared of x. So d dx of tan of some function of x, okay, is going to be the first derivative out the front times sec squared of x. Or derived using differentiation by first principles, which we'll look at later. I want you guys to leave today knowing those results, and they're all in your notes. Okay, you can turn the projector off, I won't need it. Alright. Okay, so let's differentiate the following. Example. Right. So, first one. Differentiate the following. Y is cos, 2 cos of x. Right. So what do you think the answer is going to be?
To -2 sin of x.
So?
-2 sin of x.
Yeah. Alright, so if this was 2x, alright, so ignore the cos for a moment, it was 2x, we differentiate that, we have 2. So we still got the constant number out the front, alright, so we need to include that constant number out the front, or in other words, it's really a 2, lots of d dx of cos of x. Okay? Right, so cos, so you differentiate sine, you get cos. When you differentiate cos, you're going to get negative sine. Okay, so d dx of 2 cos of x is negative 2 sine of x. Alright, y is sine 2 of x. Right, so the rule is d dx of sine of some function of x, so when it's something other than just an x there, right, is equal to the first derivative out the front of that function within the sine, cos or tan times cos of the same thing. Right? So when you differentiate sine, you get cos. Now, f of x is 2x, the f dash of x is 2, so the 2 goes out the front. Right, so the 2x stays after the cos, so it'll be 2 cos of 2x. That 3 tan of 2x plus 1. Okay, so in the bracket I can have a linear function, I can have a quadratic function, I can have other functions involved as well. Alright, the rule will work. So, when you differentiate tan, you're going to get sec squared. Right, so you've got the constant number 3 still out the front. Alright, then you need to differentiate what's in after the tan, what the function itself included with tan. Right, so f of x is 2x plus 1, the f dash of f is going to be 2, and the same function inside the bracket. Okay, and that is the equation for the gradient at the tangent at any point x on this function, this curve here. Right, so one of the main things you need to do when you differentiate is find the equation of the tangent. Right, so let's have a go at one of those. Find the equation of the tangent in exact form to the curve y is equal to sine of x at the point where x is pi on 3. Okay, so going back to our work we did towards the end of last term. Right, so the equation of the tangent, I need two things. What are they? Derivative, so I need the gradient of the tangent. And what else do I need? Need the gradient of the tangent, and I also need a point. So, y dash, so when you differentiate sine, you get cos. Okay, so at x is pi on 3, y dash is going to be cos of pi on 3. Okay, this is work itself, it's not new, just incorporating what we've done today. So pi on 3 is what in degrees?
60.
60, so what's cos of 60?
Half.
Half, same as sine of 30. Okay, so we have the gradient of the tangent. Do we have the point?
No.
Well, we've got part of it, don't we? We're told the x value, but we're not told the y value. Alright, so what you need to do is then do the y value. So y is going to be sine of pi on 3. Okay, so when x is pi on 3, y is going to be sine of pi on 3. So what is sine of 60? Alright, so now you've got your point and your gradient. Y minus y1 is equal to m outside of x take away x1. Alright, so we need this exact form. Okay, so of course, because we've got pi's and surds involved in that equation. Alright, so remember the two ways you need to represent a line. You need to either represent it as y equals mx plus b, or your general form. Okay, so unless you're told, I prefer having it in y equals mx plus b form because it's much easier to read information off that far more quickly. Okay, so I've just moved the root 3 on 2 to the other side, expanded all this out. Okay, if I want to be a bit more formal about this. Okay, I wouldn't really bother simplifying fraction common denominators because the skill is you can tell me what the equation of the tangent. You're not asked to simplify a fraction, okay? So, as far as I'm concerned, you would have answered the question at that stage there. Right, question. Okay, so nothing new, just incorporating the derivative of your trig function to be able to do your other stuff involving calculus.